on piecewise functions? Why would I have a quick little aside on piecewise functions? Look at the graphs, look at the definition of continuous, look at even the or as to the other way. Ooh, sorry if that was on the recording. The door was squeaking. The other way of showing the 3 points of the definition of continuous. Why are we pausing on piecewise functions? No idea? Look at the graphs then. I'll draw your attention. Look at the graphs then. What did we write down on the graphs? Okay, we did talk about in black what parts of the definition of continuous failed. That's what's in black. Keep going. What's in red? Yeah, what was going on? What type of discontinuity? We're going to define it a little bit more, I don't know, technically, I suppose. Today, I have the door open to get some air in here. I know some of you guys are going to get warm and going to get tired. But what I'm drawing your attention to is actually what's in blue. You guys missed it. What's in blue? Ah, now not all of them are piecewise, but how many of the 4 are piecewise? Ooh, well, if 3 out of the 4 are piecewise, maybe that's a reason for us to pause and think maybe there are some piecewise functions in section 1.4. What do you guys think? Possibly? Okay. And you're like, yeah, definitely. Some of you haven't done homework, and you're like, well, I'm not exactly sure. But if we have piecewise functions on 3 of the 4 graphs, I think they're kind of important. And yet, piecewise functions, ever since pre-cal, have been kind of complicated. So, as you guys look at the piecewise functions, can you look at the details that we put about the piecewise and figure out what type of example is missing that I probably should include at some point? What type of example is missing? Looking at the blue in the graphs, what type of example is missing?
If they both, like the part where they separate, what if they're both like on the same point where they separate?
Same point where they separate. Well, we actually have that one. Oh, I see what you mean. Ryan is saying that maybe neither of these are actually meeting up, so maybe they're both broken. So what if they actually did meet up? What if they actually did agree? That's true. It's possible that the two branches could agree. I was thinking more the inequalities. Can you guys check out the inequalities really quickly? Checking out the inequalities really quickly. Looking at the 3 examples on the page before. The first one was like, hey, you have a less than, hey, you have a greater than or equal to, or you have a less than or equal to and a greater than. You have 2 different branches, 2 different pieces. What didn't I make an example of yet? Equal to or not equal to, yeah. So we probably need to see an example of that. But for right now, let's go ahead and focus on what these ones show, okay? So on these ones, actually, hopefully you guys are writing in pen. I know you're going to be kind of annoyed with me. No, I should leave it the way it is. Let's go ahead and zoom in on this. I really want to do an example of this one. I didn't realize until right a second. Oh, no, didn't have an example of it. But that's all right. Let me get this so it's not all weird and transparent. Okay. Question. If we're taking a limit, because the definition of continuous has the limit must exist and the point must exist. If we're taking a limit, okay, of a piecewise function, the first case says, what if x is approaching a separator? Who's the separator? Any idea? If this one says not approaching a separator, why is 0 the separator? Out of all the x values, from negative infinity to infinity, who's the x that's separating one branch from the other? 0. See it? Who's the x value separating one branch from the other? 0. Okay, so 0 is the separator because he is the x value that's separating one branch from the other. All right, that's what I mean by separator. But is x even approaching the separator? No. Pause. Talk. It'll help you stay awake. Is x approaching the separator? Thank you. So then coming back, what's this look like? What if we had something like maybe this broken graph or maybe this coming together graph, but we're not even approaching C? What if we're approaching something else? Do we even have to worry about a problem? No, because on one side and on the other side, you have the exact same function. So I want you guys to check out this one. Where is 5 in the different pieces, in the different branches? Is it in the first branch, 3 minus x squared, or is it in the second branch, 4 plus 2x? Yeah, because why? 5 is greater than 0. So if you're thinking about your number line and thinking about one branch going from negative infinity all the way up and including 0, and then another branch is coming from greater than or equal to 0 and above. If we're trying to think about the number line, we're not looking at this one at all because 5 is going to be over here in this one, and specifically in the 4 plus 2x one. So thinking about the number line, since I'm only looking at the 4 plus 2x, how do I take a limit if x is not approaching a separator? Plug it in where? To the correct branch, or the correct piece. So who's the correct branch? The limit as x approaches 5 of 4 plus. And as soon as you do that, you can ignore all the messiness of that and say, oh, easy. How do I take a limit as x goes to 5 of some sort of little polynomial guy? Plug it in, plug it in. And my final answer would be 4 plus 2 times 5, which would end up being 14. Kind of like last year when we had like f of 5. What would you do? You would say, well, is 5 less than or equal to 0, or is 5 greater than 0? 5 is greater than 0. Cool, plug it in. But what we're thinking about is limits, but the idea is still the same. If x is approaching 5, which piece does it work in, the second one? It's not the separator, so cool, plug it in. Dun, dun, dun. That one's easy. Pick the right branch. What about the second one? Up here, when I was coming towards 5, guys, where would 4.9 and 4.99 and 4.999 be in which branch, the top or the bottom? Because 4.999 is greater than 0. If I was coming 5.01, 5.001, which branch, top or bottom? Bottom. So the left and right approach is still the exact same thing, which is why I just plugged in and I was done. But where would negative top? Where would positive 0.001 be? Bottom. In order to find the limit, I have to come from both sides. How do I come from both sides? Plug it into both. So I have to plug into the top, the limit as x goes to 0. I can't just say the two-sided because I have to actually split up. So I'm going to come towards 0, what? From below first? And coming towards 0 from below would be of 3 minus x squared. Then I have to come the limit as x goes to 0 from above, which would be 4 plus 2x. So I have to do the below and above. And when I do the below, what am I going to get? Yeah, because it's going to be 3 minus 0 squared, which is 3. And when I come from above, I'm going to plug in also. Just plugging in the 0, the plus or the minus, I have them in the right branch, so I just need to go ahead and now plug in. Plugging in 0 is 4 plus 2 times 0, which Thomas already said is just, is this good or bad? Yeah. Do the two one-sided limits agree? Everyone say it. Keeps you awake. Thank you. So therefore, the limit? Does that make sense? So what's different with the separator? Can anyone try to summarize what we just did? What's different with the separator? Good. You have to use both branches or plug in ultimately to both branches. That's you testing the one-sided limits. And Thomas kept going and said, and they what? The answers to the limits must do. Got it. Does that make sense? Okay. So then here at the very bottom is basically saying, what do we do with piecewise functions when we take limits? Well, when we have less than or equal to's, greater than or equal to's, less than, the or equal to's doesn't really matter for the limit because we're just saying, hey, one side, if it's a separator, one side is one limit, one side is the other limit. But if you're not even approaching a separator, just choose the branch that works and you're done. Just choose it, plug in, done. If it's a separator, gotta go from each side. So it says plug x and this in the functions on both sides. That's for the separator. Compare. If the one-sided limits agree, you can already fill this in, can't you? If the one-sided limits agree, then the limit exists. If the one-sided limits do not agree, the limit does not exist. Now I did say, what do we do with that whole not equal to and equal to thingamabob? I need your guys' help real quick. And what we just did, do you have room somewhere in that little space in your notes to write one more example, even though we kept going? Can you go to the side? Can you maybe go down below? Okay, then let's do it. If you want to turn your notebook a little bit to the side and like have it come up the page, I do that sometimes in my sermon notes because I have like a random space, but I don't want it to be next to. You can like change the orientation. Let's do one more example because as we saw on the page before, there are also these cases with the whole not equal to, and I've seen more and more kids get really confused with that. So let me do one more example. Fit it in where you can. Keep it really close to these piecewise, okay? What if we have f of x is equal to the square root of, let's do one like, if you want to look at your pictures, let's do one like graph D. Let's do one like the last graph. This will be similar to that, okay? Let's do something like x squared minus 5x plus 6 all over x minus 2. And then let's do something like 10 for x not equal to 2 and for x equal to 2. And the question is the limit as x approaches 2 of f of x. Someone tell me something that they see. What do you think we should do? What's going on? What do you see, Thomas? Ooh, he's like, I think we can factor the top. True, but let's pause and think the big picture. You're zooming in on something super specific. Why don't you factor? Okay, pause, but why even do that? What do we have to think about as x goes to 2? What I used on the page before that I think you guys kind of understood when asking you which branch we were looking at. Do you remember what I was doing with each of these numbers? What was I doing? Yeah, coming from each direction. 4.9999, 5.001, negative 0.001, positive 0.001, and thinking about the branches. Can we do that with this one? What would come from below? Which branch, top or bottom? Yeah. Top is everything but who? Everything but 2. So 1.99999, that one. Okay. Come from the other direction. Which branch, top or bottom? 2.1, 2.01, 2.001. Top. Wait, it's a piecewise function. Yeah, look at graph letter D. But everything is going to be defined by the one piece except for one point. And do we care about the at or do we care about the approach? Does that make sense? So this is actually kind of even easier than the page before. 2 is a separator, right? 2 is a separator. So true. 2 is a separator. But if we were to take this guy and have to think about towards 2 from below and towards 2 from above. Wait, remember how on the page before I was actually writing in the pieces? Just like you guys told me, they would both be this one. So do I even, like a shortcut, do I even really need to stress about writing it twice? If the trick is just to plug in the number once you have the right piece? No, I could really just do it once, ultimately, because the below and the above is of the exact same function. So actually, I can kind of take this guy, and I can say, sure, we can write it out like we're coming from each branch, but ultimately what that ends up being is really just us, I'll pretend that's a brace, just approaching 2. Now Now I am going to do what Thomas advised, which was to factor the top. We'll talk about why in a second. But I really don't even need to split up if I have a not equal to and an equal to and we're approaching that not equal to separator, because it's going to be below above the same function. Now, why did I factor it? What happens if I was to plug in and get 4 minus 10 plus 6? Ugh. So either one of these would be 0 over 0, keep going. 0 over 0, keep going. So why did I factor? Because what I want to do. And then what can I do to finish solving? Plug in 2 minus 3, so the final answer is. But I don't have to worry about the limit not existing unless it was plugging in and gets me like number over 0, infinity and beyond. Okay, that's going to be a problem. But as long as I can plug in and the limit does exist or equals 0 over 0 and I can keep going, I don't need to worry about branches of equal to and equal to. Because all I need to worry about is that not equal to equation, because he is everything but the at. He's everything but the point. And so looking back one more time, we were just looking at this function. He's everything but the point. Ignore the point. We don't care about the at anyway. Only look at the other guy, the not equal to. Okay, we've just really zoomed in on piecewise functions. It is really tricky. It's what we technically would have done yesterday if I hadn't had a flat tire. Okay, whew, here we go. Now we got to bust out some stuff. Discontinuities. Let's get technical. This is from pre-cal, basically. Technical. There are removable discontinuities and non-removable discontinuities. Which one? Discontinuities. You plug in, the function doesn't exist. Both of these. Rational functions, you plug in, the function doesn't exist. Why? Because you can't divide by 0 and have something exist. So both of these, the function, not the limit, the function doesn't exist. Which of these are removable? Keep going. Because we try to factor, we try to remove the discontinuity by reducing. So removable, those are going to be our holes. And we can see holes two different ways. We can see holes in, well, both of these have holes. This one's going to be some sort of 0 over 0. Keep going. And this is probably going to be some sort of 0 over 0, keep going, but also with a piecewise function. This is going to be like an x doesn't equal c and an x does equal c. We can call it a point discontinuity. This one's just going to look like a normal rational function, like an f of x over g of x. This one's going to be some sort of piecewise function with a not equal to and an equal to. But either way, these are going to be removable discontinuities. Non-removable. Uh-oh, I lost a sketch and I don't know where it went. Non-removable. So we just said 0 over 0 is removable, holes. What's this guy again, even though he's half erased? Maybe you can still see him. What's number over 0? Vertical asymptotes. So wouldn't that fall under this category? Number over 0, infinity and beyond. Number over 0, infinity and beyond. So vertical asymptotes, that's the last one. Oh, dear goodness me. Ay, ay, ay. Okay. It's working better than yesterday, actually. That's one type of non-removable. What did we talk about already about this guy? Right? We can put jumps up here. How do we get this? Not number over 0, but yeah, piecewise with, were you trying to explain the inequalities, Thomas? Can you guys help out? You have an x greater than or equal to, either way, c greater than or equal to, and then whoever's equal to or not equal to, the other one's the opposite. But not just any piecewise with those, but piecewises that don't match up, whose one-sided limits do not agree. Whose one-sided do not agree. So I could say more specifically, not just any piecewise, but ones where coming from below C do not agree with coming from above C. And we just saw how you do that. You plug into one branch, plug into the other branch, and compare. And then this one is that weird, I'm just going to give you one example of it, case where you have like a nasty oscillating something, something, something. Nasty oscillating something, something, something. And we haven't even really figured out how to do these by hand specifically. They're actually kind of hard to do by hand. Sine of 1 over x or cosine of 1 over x. Where you have like a number over 0. You're like, infinity! Wait, sine of infinity. Sine doing as it goes to infinity. Just thinking about the algebra, not the specific graph. But if you plug in as you go towards 0, I can show you a quick example. This is where the problem lies. It lies right at 0. As I go towards 0, wouldn't that be sine of 1 over infinity? Sorry, 1 over 0? Ugh. Plug in. Ah, but what's that? Isn't this one an error? And more specifically, infinity and beyond? But the whole thing isn't infinity and beyond, just that part's infinity and beyond. Well, whether sine goes to positive infinity or whether sine goes to negative infinity, is it getting closer and closer to anything? The y's? Or are they just bouncing and bouncing and bouncing and bouncing between 1 and negative 1 and all the values over and over and over? It's not getting like closer to anything like 0. It's not leveling off at all. So the problem, sine's just going to be forever confused. There you go. So that oscillation that never gets closer and closer and closer to anything, that's why another discontinuity, which you guys can tell, like that's bad. This would be a true DNE. But so would that limit, and so would that limit, because of the discontinuities and how they're behaving. Okay? So non-removable. All of these are non-removable. What are the only removable? Just holes, which can show up in just a normal little fraction, or it can show up in a piecewise with a not equal to and an equal to, with a fraction in there also. So what are some common functions that are continuous for all real values of x? Let me zoom in. Because if homework is going to ask you about the continuity of functions, it'd be nice to know which one. You don't even have to stress. And this is so similar to last year and the summer review packet when we talked about domain. Because isn't the domain for most functions all real numbers unless there's a problem, right? Okay, so all polynomials, all like ax to the n plus bx to the n minus 1 plus cx to the n minus 2 plus, I don't know, eventually like dx plus e, not the number. However big the polynomial is, if it's a 5th degree, 10th degree, 12th degree, 2nd degree, 3rd degree, whatever power x is, those will always be continuous. They have no domain problems at all. Continuous everywhere. Not even just continuous, even smoothly continuous, which calls them this extra term differentiable, but that's not for today. Exponential functions, whether you have something like e to the x or a to the x, and we could start throwing in other things, like what if there's a coefficient in front, no stress, still continuous, a coefficient in front, no stress, she's alive. A coefficient like up here, still good, a coefficient up here, still good. Like you can mess up these a lot. I'm going to go back to just the most basic one without all the transformations, but any exponentially dude. Even with like shifts, even with additions and subtractions and multiplications. As long as there's no division, every exponential guy, swoop, there he is. He goes forever left, forever right, continuous everywhere. No jumps, no breaks, no vertical asymptotes. Why is logarithms, why are logarithms not up here? They have a vertical asymptote and a restricted domain. They have a discontinuity at their vertical asymptote. Logarithms are continuous in their domain, just not outside. Absolute value. Yeah, no stress. If you have an absolute value of any sort of polynomial, I'm just going to put, because it looks nasty, let's just do absolute value of x. I don't know. Absolute value of x. He's fine. He's pointy, but you don't have to pick up your pencil and remove it when you're drawing his graph. You can smoothly connect, even though he's pointy, you can smoothly connect all of an absolute value. What if you put a polynomial in absolute value? It's fine. Polynomials are good. Absolute values are good. What if you put an exponential in absolute value? He's fine. Exponential absolute value. What if you put a sine? You can even make it nasty, like ax plus b or something like that. He's fine. Cosine also. Whether it's a simple one or whether it's a complicated transformed one, they're fine. They're just going to keep on bouncing. Maybe they'll be taller. Maybe they'll be squished in or spread out. Maybe they'll be shifted with the sinusoidal axis. Ooh, last year. Being somewhere else, but they're continuous everywhere. What if you put a sine or cosine in an absolute value and raise it to a power and have it in an, okay. If you put any of those together, it's still going to be continuous. As long as there are no denominators. Not division, but multiplication, addition, subtraction. Fine, 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 fine. How about these guys? Why are they fine? Radicals aren't fine. But what kind of radicals are they? What kind of roots? What's the cubed root of -8? Of -8? Cubed root of -8? What's a negative times a negative? Times a negative. You can have a negative come out of a cubed root. Because a negative times a negative is a positive times a negative is a negative. So -8 cubed rooted is -2. Negative, oh dear, hold on. I could do 2 times 2 is 4, 8, 16, 32, right? The fifth root of -32 is -2 because you'd have 5 -2's. These two would be a positive, those two would be a positive, that would be a positive, but who do you still have left to multiply? A negative. So whenever you have an odd pairing of negatives with an underneath being a negative, it's totally fine. What's wrong is when you have an even, or you need an even pairing, that should be a negative. That's impossible. Nick?
What's I squared?
I squared is square root of -1 times square root of -1, which equals -1. Yeah. I to the 4th is positive 1. Because a -1, no, you got it. I squared, I'm sorry. I squared times I squared, -1 times -1. Just come back to I being the square root of -1, and then use that. And then tangent inverse is another weird one. Tangent inverse is another weird one. But I think, didn't we put tangent inverse in our forever card? I think we did. He was that weird, like, cube rooty guy. Swoop, there he is. Anyway, he's continuous forever, forever, forever also. Okay, that's just a little sketch if you need to remember who he is. So what's coming down here below, or what's going on down here below? If you have two continuous functions, I talked about this, we just didn't write it. If you have 2 or more continuous functions, what can you do to them that will keep them continuous? You can totally multiply any continuous function by a constant, and he'll still be continuous. Sine of x or 5 sine of x, still continuous. You can take continuous functions and add or subtract them, and they'll still be continuous. Sine of x plus e to the x. X to the 5th minus the cubed root of x. Those are all still continuous. Their pieces are continuous. Adding and subtracting is not going to mess anything up. Multiplying or dividing. First, multiplying. Product property. 13 to the 5x minus 1 times sine of x. Fine. Totally fine. Multiplying 2 continuous functions, you'll still have a continuous function. But what do I have to do as soon as we talk about dividing? E to the x over sine of x. Oh, that's good everywhere but. What's the but? Bottom can't be good. 0. Good. Bottom can't be 0. Everywhere but the bottom can't be 0. So if you guys start seeing funny things being put together with adding or subtracting, just come back to who or which functions that are totally fine, do not have any domain problems, and see, are they just being added or subtracted? It's fine. Multiplied? It's fine. Multiplied by a constant? Fine. Basically, does it have transformations? It's fine. Division? Go find those zeros. It's not fine there. Okay? Now, some of you might still be writing. Let me go ahead and dual page so we can go on, because we have some examples I want us to look at. Let me see what I can do. I can, the quality might be bad, but at least it'll meet our purposes. Ugh. Oh well. It'll work. There we go. All right, you guys can go ahead and start writing down the first two examples. Discuss the continuity of each function. I'm trying to make it so that it's big. Bless you, bless you. There we go. Oh, come on. There you go. A little fuzzy, but it'll work. Let's talk about the continuity of each of these functions. Okay. What's the continuity of the first function, a? Yeah, we could do that, thinking about domain, basically. Couldn't we say that this guy is continuous? Because if you just think about 1, he's kind of in the polynomial camp. He's good. Think about x. He's a polynomial. He's good. But the problem is the division. And when you have division, just find the zeros. So this is going to be continuous for all real numbers. You could write it. But all real numbers such that x does not equal 0, right? Continuous for all real numbers such that x does not equal 0. Where a removable discontinuity exists. Ugh. You can see right where the smartboard gets mad. Must be dirt or something. What would you guys say for letter B? Good. Continuous for all, right? All real numbers x such that x does not equal 1. Now, how am I going to finish the statement, though? Where? Good. Now, wait a minute. Hold on. Why is this one removable? You can factor x plus 1, x minus 1, and remove it. Okay, then pause. What should you guys have corrected when I said it? Can I reduce this guy? No. So, ooh, this guy is not removable. This guy is actually non-removable. Careful. Gotta keep your wits about you. Can't always trust the teacher. Who's easy between C and D? Who's the easy one? D, because D is, oh, he's one of the guys that's always good. So what can I say for this guy? Yeah, he's continuous for all real numbers. Oops, if I can spell the word real. He's continuous for all real numbers. Question, does I could have a problem. What are you going to have to do to figure out whether or not this function is continuous or not? Check the limits as you come towards the separators. Check the limits as you come towards the separators. Kiddos, I want you to try homework due for Tuesday by 7 a.m. except when you hit something called the intermediate value theorem. When you hit something called the intermediate value theorem, I want you guys to go ahead and